Hi, everyone. It's a real pleasure to introduce Michael Kim, who is a postdoctoral research fellow at the Miller Institute for Basic Research at UC Berkeley, hosted by Shafi Goldwasser. Before this, Michael completed his PhD in computer science at Stanford University, advised by Omar Reingold. Michael's research addresses basic questions about the appropriate use of machine learning algorithms that make predictions about people. More generally, Michael is interested in how the computational lens, such as algorithms and complexity theory, can provide insights into emerging societal and scientific challenges. Welcome, Michael.
Thanks, Alexandra. Great, thanks for having me here. So today I want to tell you about my research on the foundations of responsible machine learning. Great. So these days, machine learning and algorithms are everywhere we look. And increasingly, they're implicated in making consequential predictions about people. Okay, ML algorithms are driving our cars, they're running advertising marketplaces, and even making medical predictions. So I like all of these examples because they're situations where historically, human decision makers have been highly regulated to ensure for responsibility. Okay, if you want to drive a car or practice medicine, you need to go out and get a license. And federal laws protect individuals against discrimination in advertising. Okay, so as we move more and more of our decision-making capacity from human decision makers to computational decision makers, like machine learning algorithms, we need to start to reason about what it even means for these algorithms to be responsible. Okay? Rather than addressing concerns of responsibility in machine learning on a situation by situation and algorithm by algorithm basis, my research program takes a more foundational approach, where we identify general patterns of behavior in algorithms, like fairness in prediction. And then we formalize these concerns that we might have into concrete definitions in the language of computer science, math, and statistics. Okay, and really a huge emphasis is on these definitions, making sure that we get the definitions right, balancing a need for general purpose solutions with an awareness for the context in which the definitions are going to be deployed. Okay, really the ideal definition would help us to clarify what we can and cannot expect from machine learned predictions. Okay, this approach really draws inspiration from the success stories of cryptography, where subtle human notions like secrecy and privacy have been formalized into concrete mathematical notions that not only come with a beautiful, rich theory, but also lay the groundwork for essential tools that are implemented in our browsers today. Okay, so in today's talk, I want to tell you about my research program, and I'll begin by discussing the central work of my research that addresses concerns of unfairness in prediction. My PhD thesis introduced and studied a notion of fairness called multicalibration. Okay, multicalibration provides a novel computational perspective on fairness, requiring predictions to guarantee certain statistical conditions over every computationally identifiable group. So as we'll see, this computational perspective enables us to provide an effective solution concept that really strengthens the guarantees of prior existing notions. Okay. In addition to multicalibration, I'll highlight two other lines of work that I've been involved in. Okay. As a postdoc, my collaborators and I generalized the idea of multicalibration and introduced this new principled framework for learning called outcome indistinguishability. Intuitively, outcome indistinguishability views the goals of machine learning through the lens of computational indistinguishability. Okay, and it turns out that this perspective, again, provides a powerful approach for guaranteeing formal properties of our learned models that are useful for reasoning about the responsibility of them. And then finally, I'll tell you about this very recent work on undetectable backdoors in machine learning models. In this work, my collaborators and I demonstrate an inherent threat to using a machine learning model that is trained by an untrusted provider. So I don't expect those terms to make sense yet, but we'll get there. These topics will form the outline for today's talk, and I'll conclude with some concrete directions for future research. Okay, so with that, I'll get started on discussing multi-calibration. So while the concern for fairness and responsibility in machine learning and algorithms is quite widespread, for today's talk, I want to focus on algorithms that make predictions about people. Okay, so a concrete example you might have in your mind is that of medical risk prediction, where we'll try to develop a predictor, an algorithm that takes in individual patients' data, pass it through this predictor algorithm, and it will spit out a predicted probability of a certain health outcome. Say the probability that an individual will have a heart attack in the next few years, okay? And we'll be thinking about this predictor as being trained on historical patient data. Okay, a bit more formally, we're going to use X to denote patient data, or individuals in this case, and use Y to denote outcomes. For today's talk, I'll focus only on binary outcomes. So for instance, a binary outcome might be, did this patient with these patient data have a heart attack or not? Okay, and given this set of individual outcome pairs, this training data, our goal will be to learn or return a predictor P that maps new individuals to estimates of the probability that this individual will have the event or not. Good. So I want to describe to you now a particular fairness concern in prediction that arises due to miscalibrated predictions. Okay, I'll define it formally in a bit, but at a high level, calibration requires predictions to mean the same thing across different groups. Okay, so in this cartoon, I've plotted two different groups, one in orange, one in blue, and at least intuitively, the predictions are miscalibrated to one another. That is, when I look at the predicted probability of my predictor on the y-axis compared to the actual probability on the x-axis, the predicted probabilities don't match up in the two populations. Okay, what is the consequence of this kind of miscalibration? Okay, the consequence is that when I set a fixed threshold on the predicted probability, I get two different group-dependent thresholds on the actual probability, okay, which can lead to a form of disparate impact where the quality of my predictions, the quality of the decisions I make based on these predictions differs across groups. If these groups are defined by protected attributes, this can be a serious fairness concern, okay? And so far from hypothetical, this kind of miscalibration has been demonstrated in existing predictors that are out there. For instance, a science study demonstrated that risk predictors that are used in the clinic today, used in hospitals to determine patients' risk and to determine triage, whether a patient qualifies for care or not, exhibit this kind of miscalibration across groups defined by race. Colloquially, it means in order to qualify for advanced care as a Black patient, you need to be considerably sicker than your counterpart white patients. Okay, so this is the type of concern that we're trying to address with this work. So the first thing you might try to do is introduce this notion of calibration formally. Okay, so formally, calibration is defined in terms of this conditional expectation of the outcome given the prediction that I'm making. Okay, but and I'll speak a little bit about this formal definition, but intuitively, I want you to think about it as saying that predictions mean what they say. Okay, so that is to say that when my predictor says that there's a 20% chance of someone having a heart attack, in fact, about 20% of the patients who I've predicted have a heart attack. Okay, so conditioned on the fact that I'm saying 20%, the average should be about 20%. Okay, so we can stare at this definition and decide whether we like it as a notion of fairness and what might be the issues with it. Okay, so the hope would be that if we consider this calibration notion, that we would pull our groups together and be able to make better decisions. The first question that we need to ask is, which groups should we be enforcing this notion for? Okay, so I don't just want this calibration to hold overall, but I'm hoping that it holds across, say, different protected groups. But maybe we do a lot of work and we try to calibrate this orange group to this blue group, but then we discover a third group, this green group, that now is miscalibrated according to our predictions. Now we have to account for them. And further, we need to start to ask, what about other attributes? Okay, so in this study that I was talking about, they partitioned the world of individuals into white patients and black patients. Didn't consider any other racial categories. And they didn't consider other categories defined by other attributes, gender categories, socioeconomic status categories. And they didn't look at how these categories relate to one another. How, when you intersect these groups, new subgroups arise that might have meaningfully different outcome probabilities that we need to calibrate to. Okay, so that's an issue with this notion of calibration that we would like to address. Okay, a sort of more subtle issue is that while I said that calibration requires that predictions mean what they say, calibration on its own does not require the predictions to say very much. Okay, in particular, I think everyone, if they spent enough time with this definition, would be able to convince yourself that it's possible to achieve this notion of calibration by outputting a single fixed value for everyone in a given group, namely the expected value in that group. Okay, so despite the fact that there might be a lot of variation in this blue group in the actual probability, there is a calibrated predictor that simply treats the group as a monolith. Okay, gives the same prediction for everyone in the group. And this, again, might meaningfully miss all of the patients in the blue group. Okay, in particular, one thing that we might indict this predictor on is that it's not calibrated on important subgroups, namely the high-risk patients in the blue population. Okay, so all of these issues seem to suggest that wouldn't it be great if we could be calibrated across every group, across every subpopulation that we could hope to identify. In that case, then hopefully, the hope would be that a fixed threshold on the predicted probability would actually correspond to a fixed threshold on the actual probability. Okay, so the question that we need to ask ourselves is, what is a meaningful notion of being calibrated on every group? Okay, is that even a reasonable thing to ask for? Okay, and this is the perspective of multicalibration. Multicalibration formalizes the idea that we can protect every computationally identifiable group. Okay, and we say that a predictor is multicalibrated if it is calibrated on every such group. I'll talk about what this idea of identifiability means in a second, but I want to emphasize that it's a qualitatively different notion of fairness than prior works. Okay, this notion of multicalibration forces you to look beyond protected groups and really reason about what's happening within protected groups. Okay, to learn across the population as a whole, and discover structure within different groups. Yes, question. So here, so good. So I'm plotting the actual probability versus the predicted probability, right? And so here, this would be great if we could achieve this for every group simultaneously. My concern would be something like here. If I set a fixed threshold here, there's lots of variation in this blue population. There's lots of actually high-risk individuals that I might completely miss if I set a threshold at the halfway point, say. And so I'm concerned that I might not identify highly qualified members of, say, the minority population. for a variety of reasons. And the question is, how do we prevent that from happening? And state that as our first order goal. That's well, so that's right, exactly. That the way this plot is depicting plots of a problematic predictor on the y compared to the actual probability. Great questions. Yes. That's right. That's correct. Right. So there may be additional features that are being measured, such that the predicted probability in that collection of features. No, it could be used in the prediction. So for instance, I guess one concrete way to think about the blue line is as every point arising conditioned on a single feature. Okay, so think of this as being defined by a racial group, let's say. Maybe I have that racial indicator in my feature set, but despite the fact that there's lots of variation in the true probability of the outcome for those patients, this predictor is not picking up on any of it. And it could be for lack of data, it could be for lack of modeling correctly, but this is the concern, regardless of how it arises. This is the concern that we're trying to address and get ahead of. Thank you. Good. So I'm proposing a definition called multicalibration, where we're going to try to enforce calibration across every group that we could hope to identify. Okay, what do I mean by identifiable here? So here in this work, we're giving a computational perspective on the idea of identifiability. We formalize this notion through complexity theory and learning theory. And intuitively, it's really giving just a minimal set of conditions for us to be able to talk about what group we're talking about. Okay, so in particular, I should be able to compute membership in these groups efficiently. So if you tell me, the way that you should tell me what group we're talking about is to give me an algorithm that evaluates set membership. So if you're in the group, I should be able to tell efficiently whether you're in or not in the group. Okay. Second is a certain auditability condition. I should be able to, given labeled data, I should be able to identify significant groups in this collection. Okay. In particular, in combination, these requirements really suggest that I should think about this collection of subgroups as being learnable. Okay, that is to say that their membership is given by functions that can be efficiently learned. Okay, so you should think about set membership as being computed by, say, conjunctions or decision trees, half spaces, maybe in the extreme, even neural networks. Okay. And once we fix this collection of functions or subpopulations, we get a parameterized definition where we say that a predictor is C multicalibrated if it's calibrated over every subpopulation identified by this class C. Okay, so this notion significantly strengthens the standard guarantees of, say, basic calibration and other group fairness notions. Okay, so I've tried to argue that this is a significant strengthening of the prior notions of fairness. What I want to talk about now is whether we can learn this thing, right? So the hope here is that we're learning over every possible identifiable group. Can we actually achieve this? Okay, so importantly, despite the strength of this notion, multicalibration can be achieved efficiently. Okay, we show this by giving an algorithm to learn a C multicalibrated predictor for any identifiable class C. Okay, the algorithm will be data efficient and uses standard tools from machine learning. Okay, so for the experts in the room, we're going to give a boosting style reduction to regression over this class C. And the sample complexity of this reduction will scale logarithmically in the number of subpopulations that we want to protect. It's to say that we can hope to protect an exponential number of groups from a polynomial size sample. Okay. So how will this algorithm go? So as I said, it will go through a sort of boosting style reduction. In particular, we're going to reduce to the problem of actually just auditing for multi-calibration. Okay, so the auditing task here is that we're given a bunch of data and our current set of predictions, and I want the auditor to tell me whether the model that I'm using right now, whether my predictions appear C multi-calibrated or not. Okay, so the algorithm is going to go as follows. It will interact with this auditor. It will say, are my predictions multi-calibrated? Maybe I start with a trivial predictor. And if it's the trivial predictor, the auditor is likely going to say, no, here's a set on which you're not multi-calibrated, on which you're not calibrated. And this will continue. I'll maybe ask again, and the auditor will give me a different set on which I'm not calibrated. Okay, and the key algorithmic insight here is to say, okay, given a set that I'm not calibrated on, how do I turn that into an update so that I can make progress towards multi-calibration? Okay, and this is what we show, that after not too many queries to this auditor, in fact, we make enough updates that the auditor is guaranteed to say yes, and we are multi-calibrated. Okay. Good. And so on a slightly more technical level, this auditing procedure, the thing that I need to tell you to finish the algorithm is how to implement this auditor. The auditing procedure is essentially equivalent to a certain weak learning problem. Okay, so a standard problem in machine learning for detecting correlations here. So I'm going to look for a function where it correlates with a subpopulation of interest that I am miscalibrated on. That's sort of the key algorithmic tool here. And we can implement that using standard regression tools that inherit the time and data complexity of this weak learning problem. Great. So in fact, this approach is simple enough that it's already been deployed by a major healthcare network as part of their COVID-19 response. And one of the things that they've done is taken standard predictors for certain health outcomes and post-processed them to achieve multi-calibration using our algorithm. Okay, so I'll highlight quickly one key case study that they ran. So what you're looking at here are results from taking a bone fracture risk predictor that has been pre-trained and then post-processed to achieve multi-calibration on CLALIT's patient population. Okay, what they're doing is they're going to achieve multi-calibration with respect to this class C conjunctions on demographic features, so a handful of demographic features. Okay, and what is this plot that you're looking at? Okay, so you're looking at a plot of calibration error plotted on a log scale. So 0, this red 0 line is the optimal thing that you would hope for. And good. In orange, you're seeing the miscalibration error before post-processing. In blue, you're seeing the miscalibration error after post-processing for multi-calibration. And now what's on the x-axis? The x-axis is plotting subpopulations from the largest subpopulation being considered on the left all the way to the smallest intersectional subpopulations on the right. Okay, so what you can see here is that initially the predictions were pretty well calibrated overall for the population as a whole, but quickly as you move to the smaller and smaller groups, the predictor was miscalibrated. After post-processing for multi-calibration, you can see that the blue curve hugs this red curve much more tightly, even on small intersectional populations like Caucasian females aged 50 to 55 from a low socioeconomic status with a history of immigration. Okay, so this is was a impressive demonstration that it actually does significantly improve calibration error across different intersectional groups. Yes. I do not, but I do not off the top of my head. I can definitely look that up. But it's what's impressive about Clalit's data set is that they have a lot of patient data. So they have a lot of patient data, and yeah. It's small in a proportion or small in absolute? It's small in a proportion. Yep. Which is significant in guaranteeing that these are not just calibrated to the data set, but calibrated to the population. Yes. Yeah, great. So actually in both a bit in the initial work and then in follow-up work, we really think about this question. And we show that actually in a formal sense, this is a no harm post-processing process. So that multi-calibration really is aligned with improving your prediction. So whether you measure by L2 or 0-1 error, for this post-processing procedure, you're only making progress towards better predictions. There's a cost in terms of data complexity. You need to actually have data to support these updates, so that I know that the updates I'm making aren't just with respect to this data set, but really with respect that they'll generalize to the population. But that's the only sort of additional cost associated with it. Yeah. Yes. Mm-hmm. Mm-hmm. Yeah.
I suppose the people who are actually what is multi-calibration in subgroups? Does it improve the situation for them to exacerbate multi-calibration when you have this sort of a categorical approach that masks further subgroups that you were not exposing?
It's a great question. So multi-calibration is parameterized not only by this computational class C, but with respect to the data and how it is coded. And so the guarantees that I can give are with respect to the information in this data that I have about individuals and groups. If that data encoding is problematic in some way, then I can't undo that here. So it could be the case that somehow bad data is masking some miscalibration. But with respect to the data that I have available to me, with respect to the information and computational resources I have available to me, I can't improve what multi-calibration says. Yes. Right, great. So the question is about generalization to the population as a whole, if I understand correctly. And so while I'm defining things in terms of sort of what I have here, we prove generalization guarantees. So that if you have enough samples, then multi-calibration on these samples implies multi-calibration in the population on the data distribution. Great question. Good. So that is sort of the core backbone behind multi-calibration and where it came from. since this initial work, there's been lots of extensions to the multi-calibration framework, thinking about it in terms of rankings, thinking about it in terms of this post-processing for different kinds of models, including neural networks, and then giving more sophisticated post-processing guarantees in terms of false error rates, and even generalizing to more sophisticated statistics than just mean prediction. So that I'm happy to take more questions, and I'm happy to talk all day about multi-calibration, but that's what I have time to talk about today. Next, I want to tell you about this idea of outcome indistinguishability, which is a new solution concept for machine learning. Okay, so typically, traditionally, we think about learning in the framework of finding a best fit predictor, okay? Where we have some data and we want to fit a model that captures the data, right? And so this fit is typically determined by overall performance. Anything like fairness is viewed as a constraint that inhibits the performance of the model. Multi-calibration kind of flipped this on its head and said, actually, the thing that we want as a first order goal is fairness. And the question that we ask here is whether we can generalize this approach and generalize sort of how we think about the goals of learning. Okay, and so while this research is about machine learning, here we're going to borrow a perspective from our cryptographer friends, which is the perspective of computational indistinguishability. Okay, indistinguishability formalizes the idea that different objects, random objects, can be meaningfully different, but look the same to efficient distinguishers, to efficient algorithms. Okay, so this really motivates the idea of outcome indistinguishability, and I think it's best described as the following game. Okay, I'm going to present to you in this game a triple of an individual x, a prediction p tilde of x, and an outcome y. Okay. In addition, I'm going to promise you that this outcome y is sampled from one of two worlds. Either the outcome is going to be sampled from nature, from the real world, and I'll have a real outcome according to this individual x. Okay. Alternatively, in the other world, I'm going to sample this outcome according to my predictive model. Okay, so y will be sampled according to p tilde of x, this probability that I've already exposed to you. Okay, now comes your job. Your job is to guess which world we're in, to guess whether the outcome was sampled according to nature or according to my model of nature. Okay. Intuitively, a predictor is outcome indistinguishable if you can't win this game. Okay, if you can't distinguish whether the outcome was sampled according to nature or according to the model of nature. Okay, so while this game is really simple to state, as we'll see, it provides a powerful framework for learning models. A bit more formally, we're not just going to rely on the audience to distinguish our outcomes. We're going to use so-called distinguisher algorithms. Okay, so these algorithms similarly will take in an individual prediction outcome triple, and their output, will intuitively be a guess as to whether the outcome was drawn from nature or from the model of nature. Okay, and then collectively, we're going to build up a collection of distinguisher algorithms and require that our predictions be indistinguishable to all of these algorithms simultaneously. Okay, so for a collection of distinguisher algorithms a predictor is A outcome indistinguishable if for every distinguisher in the class of algorithms, for every D in A, the expectation of the distinguisher's behavior under nature's distribution is roughly the same as the expectation under the modeled outcomes. Okay, here I'm taking an expectation not just conditionally on the outcome, but also an expectation over individuals X. Okay, so this is, again, is a parametric definition, but the thing that I want to emphasize here really emphasize is that the collection of distinguishers that I define will completely determine the quality of this OI guarantee. If I define a very weak collection of distinguisher algorithms that don't do very much, then it will be a comparatively weak definition. On the other hand, if I define a very strong and expressive collection of algorithms, then it could be a very strong guarantee. Okay, so what I'm going to do next is go through a number of different properties that you might want of a machine learned predictor and show how to derive a class of distinguisher algorithms such that outcome indistinguishability implies this property. Okay, and we'll go through a number of traditional learning goals as well as show how to achieve properties that, at this point, I don't know any other way to get other than through outcome indistinguishability. Okay. Good. So whenever we have a new concept, it's good to compare to the old. So in particular, we should compare the guarantees of outcome indistinguishability to a more traditional approach like loss minimization. Okay, loss minimization is this central paradigm of best fit prediction, where we fix a loss function L and a hypothesis class H, and we aim to learn a predictor P that achieves loss that is at most the best loss achievable in this hypothesis class. Okay, this is the standard. If you've used a machine learning model, you've probably used a machine learning model trained via loss minimization. Okay, how does this compare to outcome indistinguishability? What we show is that outcome indistinguishability is capable of capturing loss minimization. That is, for any loss and for any hypothesis class, I can write down a class of distinguisher algorithms, which I denote A sub LH, such that this A sub LH outcome indistinguishability implies loss minimization. Okay, I've written it down here. For the sake of this talk, I don't need you to worry about what exactly this class of functions is. But the point is that it's an explicit class of functions that I can write down and reason about. It's a concrete, feasible class of functions where intuitively the distinguishers, what they're doing is evaluating the loss function over different hypotheses in the class and over the predictions. But once I have this explicit class, then I can implement loss minimization via outcome indistinguishability. Okay. So this is to say that outcome indistinguishability implies loss minimization. How does this proof go? Well, in fact, it comes from thinking about an even more general problem. So it comes from a recent work where that introduced the idea of an omni-predictor. Okay, an omni-predictor is a really strengthened version of loss minimization, where we look for a predictor that is not just a loss minimizer for a fixed loss, but is a loss minimizer for a collection of losses. So it will give the loss minimization guarantee over a collection of losses simultaneously. Okay, so here I'm given a collection of losses L and a hypothesis class H, and I want my predictor to give me the loss minimization guarantee over every loss in the class simultaneously. Okay. And using this outcome indistinguishability perspective, we can simply reuse the distinguishers from our loss minimization guarantee originally and just take the union of these distinguishers and immediately get this omni-predictor guarantee. Okay. I need to incorporate, on a technical level, I need to incorporate a post-processing that type checks my prediction to my loss. But on a technical, importantly, the point is that I'm able to get this new guarantee, this omni-predictor guarantee, simultaneous loss minimization over a collection of losses with very little work once I had the loss minimization guarantee from outcome indistinguishability. Okay, so pushing ahead, it's not surprising that because outcome indistinguishability came out of the study of multicalibration, that it's also capable of implementing multicalibration. So, and again, I'm going to define a different loss class or a different distinguisher class here where the distinguishers are going to run different calibration tests over my different subpopulations. Okay. Finally, I want to talk about an idea called universal adaptability. Oh, yes. Thank you. Mm-hmm. Mm-hmm. Yeah. So it's a great question. So the question is whether, whether these notions are feasible simultaneously, right? In some sense, that can I achieve these and other notions? So what you'll notice is that actually for the notions that I'm going to put up here today, there is a simple demonstration that they are feasible, and by the fact that the statistically optimal predictor will satisfy all of the notions. What that means is that there is a point that is feasible for all of them simultaneously. So if I took the union of all of the distinguishers that I defined today, I could get a predictor that satisfied all of these notions simultaneously. In general, that may not be true. And it's a great question to ask, why are these notions feasible? And how do my different distinguishers interact with one another? But for today's talk, in fact, I could, edit my slides and write down distinguishers, a collection of distinguishers, an explicit class that I could audit that would guarantee all of the properties simultaneously. Thanks for the question. Great. So the final notion that I'll talk about today is called universal adaptability. Universal adaptability is a certain robustness guarantee, distributional robustness guarantee, that is motivated by saying maybe we have a single source of high quality data, but we want to deploy our insights from this maybe large medical study across the country, across the world, in settings where our populations may differ meaningfully from where we started. Okay, and can we do that in a way that doesn't require reweighting for each population? Okay, and again, what we show is that there is an explicit class under which outcome indistinguishability guarantees this formal notion that we formalize through the lens of propensity scores. Okay, and we have a case study showing that this actually works in certain health contexts. I want to push ahead and wrap up with outcome indistinguishability. The thing that you should all be asking me is, I've talked all about how great this notion is and what we can get with it, but how do we get outcome indistinguishability in the first place? Turns out that the connection between multi-calibration and outcome indistinguishability is strong enough that we can actually reuse the learning algorithm that we discussed for multi-calibration basically off the shelf to guarantee outcome indistinguishability. So again, by the feasibility of multi-calibration through this auditing framework, we can see the feasibility of outcome indistinguishability. Great. So in the last few minutes, I want to switch gears and talk about this work on undetectable backdoors. Okay, and in this work, we're not just going to think about computational indistinguishability, but we're really going to draw from cryptography in this way of adversarial thinking, okay? Where I'm going to put on my adversary hat and say, how can I attack some of the existing frameworks in machine learning, okay? So in particular, we're motivated by this problem in sort of thinking about machine learning as a service. Okay, these days, training machine learning models can be really expensive and require expertise. right? If you want to achieve fairness and outcome indistinguishability, maybe you need an expert to train that model. Maybe you just need a lot of computation. So a common solution to this problem is to delegate training to a party. Okay, so the scientist maybe is a great scientist, has a bunch of data, but doesn't know what to do with it. And so asks the service provider, hey, can you learn a machine learning model for me? Service provider says, sure thing, and sends it back over. Question, though, is why should this scientist trust this service provider? Often, the party that we are delegating to is fundamentally untrustworthy. Okay? And the question that we ask in this model, in this work, is what abuses can an untrusted, malicious service provider exert against the scientists? Okay? So what we show is a potential abuse by such an untrusted party. Okay? We do this by defining the notion of an undetectable backdoor. Okay? As the name suggests, an undetectable backdoor has two components. First of all, it's a backdoor. It provides a mechanism to change the output of a machine learned predictor on any possible input. Okay? Second of all, it's undetectable. Okay? What this means is that it is hidden to the scientist, hidden to a client using cryptography. In other words, it's impossible to detect using feasible algorithms. Okay? A bit more formally, undetectable backdoors are formalized through three algorithms. The first algorithm we call honest train. This is the honest training algorithm that we agreed upon. If you run this algorithm, then the model really will be trained to my specification. The second algorithm is backdoor train. Okay? This is also a training algorithm. It's also an algorithm that returns a machine learning predictor, P-dagger in this case. Then the third algorithm is called activate, and it's involved in the backdoor mechanism, which I'll describe now. Okay, so what this backdoor mechanism is it says, using activate, I can go from X to X prime, which is a very small, imperceptible change. But in the backdoored model, the classification under this model will be very different, will be wrong, will be flipped from what it should have been. And I should be able to do this for every possible input, every possible individual in the domain. It's when I'm evaluating an X. If I'm evaluating on X, you give me any X, I can change it to an X prime such that I can flip the sign from P dagger of X and P dagger of X prime. So this model will have a flip for every X in the domain. I don't need to know the backdoored inputs ahead of time. All of the inputs will be backdoored after this construction. And then second, the property that makes it undetectable is that the honest model P and the backdoored model P dagger are computationally indistinguishable. Okay. Yeah. Good. So the question is about the perturbation model. I'm not claiming any undetectability of the perturbed inputs. What I am claiming is that P and P dagger on their own are computationally indistinguishable. The perturbation model that we'll use and whether those are undetectable will be inherited from the sort of adversarial example space. So, making a small change in L2 or L0. The defender might know that that is the metric that we're using, but doesn't necessarily get to see X and X prime. Yeah, great question. So it's computed in the cloud, but then handed over to the user. Yes, so I'll describe exact. P is. Yes. Yep. So the result that we have a few different results in this space. But what we show is that this threat of undetectable backdoors is widespread, that there exists a white box undetectable backdoor for, in this case, for a certain random feature network. But this undetectability, this guarantee is undetectable even given a full description of the neural network. Okay, so this is a training algorithm for learning a one hidden layer neural network. What I'm going to do is train the model, hand it over to you. You can run it, you can inspect it, you can do whatever you want to it. You can see exactly the connectivity and the weights, and still you will not be able to detect whether it is backdoored or not. And the way we do this is actually conceptually very simple. We're going to run the honest training algorithm, basically as is, except for sampling our randomness from a certain dishonest but indistinguishable random distribution. Okay, so I need to push ahead, but for the experts in the room, we're training using this random Fourier feature framework. The honest training algorithm in this case samples from Gaussian randomness. Okay, what are we going to do? We're going to sample our random activations from a certain Gaussian pancakes distribution. Okay, what is this Gaussian pancakes distribution? Well, it's a distribution that is a bona fide Gaussian in every direction, but for one direction. Okay, and in that direction, it's stacked up periodic, really thin pancakes. Okay, so maybe you can see every once in a while there's this stacked up, aligned direction. Okay, what we show is that using that periodicity in this Gaussian pancakes distribution, we can make a small perturbation that will flip the sign of these cosine features. Okay, but importantly, this Gaussian pancakes distribution and the Gaussian distribution in high dimensions have been shown to be computationally indistinguishable. Okay, that is that unless you can break the underlying assumptions for, say, post-quantum cryptography, like you will never be able to tell whether your samples are coming from the Gaussian or the Gaussian pancakes distribution without knowledge of this secret direction up front. Okay, so which is to say that the weights that we learn and hand over to the client look just as good as the Gaussian distribution. They'll never be the wiser. Okay, so I want to, in the interest of time, push ahead to some concluding directions for future research. Okay, so I've talked about a notion of fairness called multicalibration. And the first direction that I propose for future research is to study effective definitions of fairness like multicalibration in settings where predictions have consequences. Okay, so existing works on fairness mainly think about prediction in the supervised learning setting, where there's a fixed distribution on inputs and outputs. Okay, often, however, the predictions that we make actually affect the outcome distribution that we observe, right? So for instance, if I'm using a predictor to inform your medical treatment, stands to reason that based on the prediction, I might take a different medicine or take a different treatment, which in turn might affect the distribution on outcomes for the patients. Okay, and so in fact, like this is often the point of prediction, to affect positive change in individuals' outcomes. Okay, in this setting, it's been formalized recently in as so-called performative prediction, this setting where predictions can influence the outcomes that we aim to predict. In this setting, it's not even clear what we mean up front when we say like we want accurate predictions, let alone when we want fair predictions. Still, I propose that the multi-calibration framework can be applied to this performative prediction setting, and more generally to prediction settings where there's complicated feedback loops in predictions and where individuals may hold diverse preferences over the different outcomes that are possible. Okay, and so in some initial work, I've made some initial progress with a Berkeley graduate student recently, trying to understand what this might mean. but there's still a lot of both conceptual and technical work to be done here. Second, the second direction that I propose for future research is to develop the theory of outcome indistinguishability further. Okay, as we've seen, outcome indistinguishability is capable of guaranteeing a diverse set of guarantees. But a natural question then to ask is, like, what else can we guarantee in this framework? To answer this question completely, I aim to build a unified theory of the complexity of learning via outcome indistinguishability. Okay, so actually many of the existing works that use OI as a way to guarantee some downstream property, they leverage very similar arguments in going from saying why indistinguishability gives the desired property. Okay, I propose that many of these arguments can actually be abstracted away and built up into a single theory. And so if successful, this theory would make it easy and almost mechanical to go from a new property that you would want in a machine learning predictor to a proof of why outcome indistinguishability can give it to you and what the complexity of achieving it via this notion would be. Okay. Finally, the work on undetectable backdoors presents a clear threat and a clear breach of trust in evaluating and using a machine learned model when you are not the trainer of the model. Okay, so while it's important to know what threats are out there, ultimately my goal is to develop ways to mitigate these threats. Okay, so the question we need to ask is, how do we extend the frameworks that we're thinking about in a way that might allow for this? Okay, so to address this and other threats in the setting of machine learning as a service, I propose to build cryptographic proof systems for certifying formal properties in machine learning. Okay, such proof systems would really build off of the literature in cryptography for general purpose delegation of computation, but ideally would leverage the structure and the properties available to us in machine learning to give more efficient solutions. Okay, more generally, I believe that we need to think through new models for delegation of computation in the context of machine learning to ensure that whenever we obtain a machine learning model, we can trust that it has been trained responsibly. So thanks so much. I'm happy to take any other questions. Yes.
So you show that there is and at the end you would propose that there could be some cost of that. Elaborate more about that could require to detect or prevent the
Certainly. So what we show at this point is that if I train the predictor completely on my own and send it over to you and hand it to you, even in the clear, then you will not be able to tell whether it was trained with the Gaussian or Gaussian pancake. That doesn't preclude us from interacting in some meaningful way as I'm training the model in a way that you would be able to certify the end result. Okay, so really the problem here is that I'm handing this model to you, and really you have to run some non-trivial circuit analysis over this model, right? All on your own. We know from complexity theory that interaction in this way can be very powerful, that you as the verifier can verify much more complicated statements than you're with my help, even if I'm a malicious prover, even if I'm a malicious trainer, that you can be certain of much more complicated statements than you could be on your own. So I think this is one direction to really think about, is how to force the prover, how to force the trainer to interact with you in a way that will give more meaningful results. I think another avenue that also comes up in cryptography is not just using a single provider, but using multiple providers and trying to see how you can force them to catch them in their lies. Yeah, great questions. Yes. Mm-hmm. Yeah, so the undetectability guarantee guarantees that under efficient checks, under efficient tests, the model will behave exactly the same. The point is that without the backdoor is only activated when the adversary uses this malicious activate function. Okay, yeah, so it could be known to you, but one thing that I elided for simplicity on the slide is that there's a secret key associated with the activate function. Okay, so and without knowledge of the secret key, you'll never know how to activate the inputs, and you'll never be able to witness the fact that it's backdoored on your own. Great questions. Yes. Mm-hmm. Great question. So in the context of the do no harm theorem that I'm talking about that we proved, this is only in the context of accuracy that we're talking about. However, multi-calibration is compatible with differential privacy. So in fact, the way to get the strongest guarantee on the sample complexity of achieving multi-calibration actually goes through differential privacy. So in this sense, accuracy, privacy, and fairness are all aligned in this context. Great question. Yes.
Again, you talked about marginalized and abstract societal vision of make progress on it, and I think that's a powerful approach. But I'm also wondering what you think is lost. So when you think of concept like fairness, I don't know whether it's something like multi-calibration. Other or not.
Totally. It's a great question. I think the reason to introduce formalism is so that we can talk precisely about what we're talking about. So I can tell you, like, I can say, like, is your predictor multi-calibrated? Generically, I can't tell you for a given context, are your predictions fair? I can tell you, though, whether it's multi-calibrated. And so for me, I think multi-calibration is a very powerful notion. And I want to know, suppose your predictor is not multi-calibrated. Why is it not multi-calibrated? What are you doing? Is it not multi-calibrated because you haven't worked hard enough, or because you haven't considered fairness? Or is it not multi-calibrated because you're using a different notion of fairness and you believe that to be more appropriate for this context? And what we've shown, one of the results that I didn't have time to talk about, but says that actually learning a multi-calibrated predictor and then post-processing it for some of these other parity-based notions of fairness actually gives you a very meaningful downstream guarantee. So certainly this is not the only notion of fairness, but I think it's part of the conversation. And I think the power of abstraction and definitions is allowing us to talk very precisely about issues that often aren't precise or require nuance. Thanks. Thanks so much.